All right, lecture 6. So let me start by a brief review of what we went over last time. Today I'll try to cover more, and that's why I'll do a shorter summary of the last lecture. But let me just say a few words about the structure of the course is. So we talked about locality in 2 lectures, right? We said this is a principle of field theory. Another principle that we mentioned is symmetry. So this was section 2, I guess, section 2 of the course. Symmetry will consume us for a while. Section 3, 4, and 5 of the course is going to be about symmetry. So here was about the action principle, right? And similarly, I'll give you something to hold on to. And then by the time that we've gone through symmetry, we'll be done with classical field theory and we'll be halfway through the semester. Right? Okay. So locality was about the action principle, and well, action principle is not necessarily local, but locality has to do with the fact that the action is an integral of a density. The space dimension in this one? Yeah, I don't remember. Right? So this is a function of the fields and their derivatives, right? So this is a density. That's locality. Now, a lot of stuff that I say now, of course, is to start. As we get more complicated and more elaborate in part 2 of the course towards the end of the semester, we'll go back and revisit some of these issues, right? But I want you to hold on to these. All right. We gave some examples in the last lecture. That's what we did. So I'll not repeat that. Those examples, I'll not go over them again. But we gave examples of these Lagrangians and locality. So part 3 of the course, I want to, similar to this action principle on this picture, I want to give you guys some picture to hold on to. And the picture is this. So symmetries, it's like a triangle. Conserved charges. And here is representations of groups. Representation of groups. Lie groups and Lie algebras. Okay, representations of the groups. And they're all related. So we'll go through different aspects of these. And what I actually mean here is, I mean continuous symmetries. And then here I'll put Lie groups. And here I'll put conserved currents. Okay? So that's the triangle to have in mind. What do I mean by continuous? I don't really mean continuous. I mean differentiable. So I'll clarify that. Conservation laws are about these conserved currents. And these Lie groups and Lie algebra representation theory is also another aspect of it. So this is a triangle. We'll talk about Wigner's theorem, which is a connection between representations and symmetries in quantum mechanics. Do you guys know anyone already? What's Wigner's theorem? It says symmetries are represented unitarily on the Hilbert space or anti-unitarily. We'll talk about Noether's theorem, first Noether theorem, that connects continuous symmetries and conserved currents. And we'll talk about the connection between the Lie algebra generators and their commutators and the commutated Lie algebra of conserved currents. We'll comment on that. So every aspect of this we'll cover. Now, the connection between symmetries and conserved currents, we will split the discussion into 2 parts. We'll talk about Noether's first theorem, which is the case of global charges. I'll define those words. And then we'll talk about Noether's second theorem, which is about the setups like gauge theories, where you don't really have a symmetry. You end up with this made up imaginary symmetry transformation that's unphysical, just because you insist on locality, and that has consequences. So if you want, in that case, this would be a constraint that's connected to conservations. Right? That's Noether's second theorem. Right? So that's the plan of this section 3. Today we're going to talk about just this part. Differentiable symmetries to conserve currents, Noether's first theorem. Questions? So this is a plan for today. All right, here it is. Noether's first theorem says the following. To every differentiable symmetry transformation, this is colloquially, right? Of a local action, there corresponds a conserved local current. Right? You see the word local all over, right? So to every differentiable symmetry of transformation of a local action, there corresponds a conserved local current. So we're talking about actions and local actions. And what comes out of this analysis is a conservation law, which is a local equation. Good. Don't want to comment on that for now. No, I'm all right. Okay, good. What this will not cover is, so here an important word is differentiable. This Noether's first theorem or second theorem, it does not say anything about discrete symmetries. Right? These are continuous and differentiable. I'll define what a differentiable symmetry is. Transformation is. All right. Do you guys know what a current is? Conserved current. If you were to define it. I'll make sure I'll comment on it. No? A current is a field, an operator, right? A local field or local operator that satisfy that, well, of course, it transforms in some representation of the Poincare group, like all fields, right? So I'm going to call it J. It's conventional to call it J. And it has a bunch of indices here, right? Mu1, mu2, mu n. These are Lorentz indices. Once we get to the representation to your Poincare group, we talk about that. It satisfies the following equation, conservation. It has 0 divergence, 4 divergence, right? That's conservation. So that's every operator of this type that satisfy a relation like this, we call it a conserved current. All right. And it's a local equation, right? This is defined at every point in space-time. All right, let's back up. What are classical fields? I'll try to, at first it might seem like what I'm doing is a little bit too mathematical, but believe me, this saves you a lot of confusion later. What is a classical field? It's a map from space-time, manifold M, to complex numbers if it's a complex field. So this is, for example, a complex scalar field, right? So every point to a manifold, it associates a number. More generally, we can have a collection of fields that we label by A, phi A. These are all maps from M, from the space-time to complex numbers. And then we are going to write, as we said, principle of locality, an action, which is a sum over all fields A of an integral of this form. This is the action that we've talked about, right? All right. But I have to first define what these two things mean. It seems like at the moment, I haven't told you what X is, right? A point on a manifold is a point on a manifold, is P. But I wrote an integral over X. X is the coordinate system. It's a chart that I pick. And I can pick my chart, you can pick your coordinates. You have to write an expression that's sensible, right? Good? You're with me? Yeah. 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 Oh, yeah. I'm assuming that there are no interactions for now. This is just schematic, right? None of it would rely on that. Yeah. I'll mention that. For now, I define the field as a map from the space-time manifold to complex numbers. It's important, right? Because if I want to talk about derivatives or differentiation or variation, I have to make sure I know what my coordinates are and what the deal is. All right. So let's ignore that for a second and pretend we all know what 5x is. Right? I'll come back to that. We're going to be interested in a set of transformations of the field. There are two types of transformations we could do. We could do internal transformations. These are transformations in that label A, phi of A, right? For example, you could at every point rotate. You might have two fields at every point and apply a rotation in between these 2 points and two fields at every point in space, such that doesn't depend on space, right? This is an internal transformation. It has another name. Anyone knows what it's called? Global transformation. It's called a global transformation. Global because it has no dependence on space. It's like this. The simplest example of this is I have is this. Take oh, we don't know what's Fermi on this. Oops. Never mind. I don't have any simple examples. Yeah. So internal transformations are those. Then we have space-time transformations. An example of space-time transformation. These are things that act on coordinates, right? For example, Poincare transformations are space-time transformations, right? In general, we're going to be interested in transformations that are combination of the two. We both transform the space points and the fields, right? Our transformations are a combination of the two. As a matter of fact, that's the stuff that we should always consider. Good. So under the transformations we're going to consider, the point x prime, x goes to x prime, but also the field phi goes to phi prime. Now we're going to be talking to simplify things. We're going to be talking about infinitesimal transformations, right? So imagine for now we're physicists, so we can just take derivatives arbitrarily. Yeah.
So here the phi 1 and phi 2 are two different things.
Yeah. For example, a complex theorem.
All space and transformation are concurrent.
In this course, yes. Yeah, depends on your space time. So in this course, we're talking about flat space quantum field theory, or field theory, which is your space time are. Well, I'll define what they're actually. They are the isometries of your manifold, your metric. Do you guys know what an isometry is? It's a transformation, it's a diffeomorphism that leaves a metric there. Yeah. I'll define isometries very formally in a second. Good? Are we good? Okay. In general, for a variation in space-time coordinates, in space-time, we're going to use this notation of delta x mu. And for a variation of the field, we're going to use the notation of delta phi. And I'm going to use, this might sound confusing, this capital delta for an infinitesimal transformation that applies both, that changes both the field and the space-time, right? Internal and space-time. You should always consider both at the same time. It's almost nonsensical to only talk about space-time transformations. If you're lucky, that's sensible. When does that work? When your field is a scalar field. When your field is not a scalar field, it's nonsensical to talk about, okay? The field also transforms, always. Scalar field is set up where it's transformed trivially. All right, good. Very good. So let's also say that delta x mu is an infinitesimal change in the space-time, an infinitesimal space-time transformation. So let's introduce some abstract infinitesimal variables, epsilon i's, and expand it this way. These are independent infinitesimal variables, and you could do the same for the field phi. If this is a little bit weird at the moment, don't worry about it, because I'm going to work out examples. But it should be kind of easy to see what I mean by that, right? For example, if you have a translation, what is the analog of what I'm doing? An infinitesimal translation sends x mu to x mu plus epsilon mu, right? So my delta x mu is epsilon mu that I can write as, how do I want to write it? Is that how? Oh, I called it I x I mu. What is xi mu? Delta mu I, right? This is just for translation.
Okay. Like usually you would write it like partial x whole, partial x.
No, well, all I did was that I just wrote, yeah, I just want to introduce these variables that are independent. You'll see the advantage of this, because I want to write down an expression for the Noether current. At the moment, it seems like weird to do this, but as you start working out examples, you see this good notation. The same holds for the field. All right. So we defined our local transformations. All right, so these are our local transformations. What is a symmetry? We say we have a symmetry if under one such transformation, the action is left invariant. The action, right? It's important. The action. Delta of S. This delta, by the way, is an infinitesimal, right? This is my notation for infinitesimal. What are the consequences of it? We're going to see that today, but just to tell you in advance that every time you have a symmetry transformation, so here's the way you characterize a transformation, right? If these transformations leave the action invariant, for each independent transformation with label I, you get a conserved current, J mu I. This is the conservation law. By the way, hopefully this is clear. Why is this a conservation law? Because this is del T of JT. I don't know, I remember what my notation was. Right? Or J0, I think I called it. Okay. J0 of I is a charge, it's called the charge density. This means that the change in the charge density is equal to the gradient of it. That already tells you it's a conservation law, meaning that if you draw, let me erase this. In space, if you draw, so here's a Cauchy slice. If you draw some ball in space, the change delta t of rho here is equal to the amount of current that flows in. That's the conservation law, right? Del t of rho 0I is equal to the divergence. It's also a continuity equation in space-time. All right, so that's why we call J0 or the T component of this charge density. We're also going to define it every time we have a conserved current, we can define a conserved charge accordingly. How do you do it? You take some sort of a surface, co-dimension one surface, right? Say constant time slice, and integrate your charge density. Once you have a charge density, you integrate in space, you get charge, right? And the conservation law tells you that the charge is d dt of qi is 0. We'll prove all of this, right? But that, I'm just telling you in advance what are the inputs and outputs of the theorem. So the input is a local transformation that we define. It simultaneously transforms the acts in space-time and the field. It's a symmetry if it leaves the action invariant. And the consequences of it is that there will be operator J mu I that satisfy that equation, and that has a physical interpretation of conserved currents. Good? Yes.
What does that I represent?
These are independent transformations that leave the action in there. So I write down a transform. You see, I wrote down delta x mu. I erased it. Is that one conservation law? Is that two conservation laws? It's actually d+1 conservation laws, because I can pick the label to be in the x direction, in the y direction, in the z direction, time direction, right? This I labeled independent guys. Now for translations, the label I could be also used for like you could label I by space time because I reduce delta mu I, right? But in general, that's not the case. That's why I introduced this label I. Like for example, when you have a rotation, like let's say you have only let's say you're in you only have rotation in space, right? You only have one conserved current, right? But then the corresponding guy has all sorts of mixes x1 and x2, right? To each transformation that leaves the action invariant, independent transformation that leaves the action invariant, there corresponds the conserved current. What does independent mean here? When I wrote it this way, it meant that I could pick epsilon i's as I wish. I could pick as many of them as I want to 0, keeping some of them non-zero. So if I keep one is non-zero, the rest 0, right? I get a conservation law. Make sense?
So it's like a linear combination of this epsilon.
What's that?
Right? It's like a linear combination.
Yeah. All right. Any questions? All right. I'm going very slowly, but I want to make sure. All right. Let's talk a little bit more about charges and currents. We're in Minkowski space in this course. Minkowski space is flat RD, like for example, 3 + 1 dimension, R3 times RT. RT is just time, right? That's your manifold. Often we define charges by integrating the current density, the charge density over space, right? So we take space-time, we introduce some initial hypersurface, Ti. Remember, we've gone through this many times. And then T final, we integrate the charge density over Ti. That is defined over this surface, 3-dimensional, d-dimensional surface. We could do that for later at time f. And conservation law tells you that the two values are the same. The two are the same operators as operators in the Hilbert space. Well, I'm not like quantum field theory, sorry. They're the same values. This is classical field theory. How do I know that? Well, we'll see that this is a consequence of the conservation law. I can write down the value of charge here minus the value of charge here as an integral of the divergence of the current over this region. And if the divergence of the current vanishes, the charges cancel. Right? That's the connection between conservation law for conservation of charge and conservation of current. This hopefully, let's make sure this is important. So currents live at every point in space-time. Charges live on codimension one surfaces, on codimension one surfaces. Right? Usually think of that as like constant time. But it doesn't happen. We'll see examples of actually I think you will see examples of non-constant time charges. Do you have any examples already? Well,
with those sim charges.
Call it no, simpler than that. Simpler, much simpler than that. Okay, well, think about boost. All right. Now, by now you've seen two setups, two statements that have to do with the variation of the action being equal to 0. The first one gave us equations of motion, right? It came from the fact that it came from the least action principle. That was called, yeah, least action principle. We wanted to extremize the action, so we took a variation of the action with respect to an arbitrary field transformation. We set to 0. We read off the equations of motion, or Lagrange equations. Now we're doing something similar. We're doing some general transformations, focusing on those that have delta S equals 0. How are these two different? They're different in the following sense. This is absolutely crucial. When we did the variation principle to read off the equations of motion, I discarded the boundary term at infinity. I threw that out because the fields at infinity vanish, or some boundary condition that's set. I set the boundary terms were non-zero. I just set them to 0 by my boundary condition, and I threw them out. And to do that, I have to push them all the way to infinity. Or I have to put some silly, crazy Dirichlet boundary condition finite distance. Here, the boundary terms vanish, cancel, period. There are no boundary terms. They just cancel. There are boundaries, but they cancel. You don't need to go to infinity or do anything like that, right? If you draw a ball like that, for all regions of that type, you will get variation of the action 0. Right? This is very, very important. So this already, there's a nice interplay between Euler-Lagrange equation and conservation laws, but hopefully this is clear. So delta S was equal to 0 in the action principle for the whole space-time. We had to discard things all the way to infinity. Here we're not doing that. The boundary terms, not only that, the boundary terms will cancel. Questions? Thoughts? Comments? Yeah. Go ahead.
So just to clarify, like for the symmetry type stuff, like if you draw any boundary, the boundary terms will cancel.
So I did this is so what was the example I worked out? Sorry, this might be misleading. I'm sorry. I think this picture might be misleading. I worked out this example. This is time and this is space. ITF. Right? And basically the statement was that I defined some Q here, Q of F, Q of I, and Q of F minus Q of I was the integral over the whole inside, right, of del mu J mu of X, right? Good. Now, when I say that the boundary terms cancel, I just mean that I didn't have to take these boundaries. I can take anything like this in space-time. It doesn't matter. If this vanishes, the integral over this will give you 0. Right? So here,
That's
I
like
picked
the divergence there.
yeah, it is. It is. I'll get there. We'll prove that. It is a divergence here. Yeah.
Okay, no, I think you haven't mentioned that, but this total derivative is the one that we would introduce into the action integral.
Sorry, which total derivative?
The total derivative of the del mu, j mu.
Oh, for now, forget about this. But yeah, go ahead. Go.
So you have a total derivative that you can introduce in the action without any consequences. Or that you can
No. At the moment, I don't know about this at all. I just made a transformation, and I told you that if that transformation leaves my action invariant, I will cook up for you some J mu that satisfies this equation. I'm not adding anything to the action. Maybe the way I presented it was a little bit weird.
So
I was
this is
just
a
trying
consequence.
It's a consequence. There was a theorem that says if you have a symmetry, then this exists. We'll prove that. I just wanted to tell you what is the input and output of the theorem first.
Oh,
Right? I'm not adding anything to that. Sorry, maybe I presented it weird. Yeah.
Here, we are saying that if we have a symmetry, meaning this del S is equal to 0,
Yeah.
that automatically guarantees that converter reduction.
Yes, we'll prove that. All right. Good. Now that I've said that, let's just rewind and do some define what a differentiable transformation in space-time is. As I said, I already said this, it might seem somewhat abstract, but I absolutely guarantee you it will save you tons of confusion. This I learned the hard way. People talking about passive and active transformation is a headache, right? So here is one time forever. I'm going to try to explain it. So consider a space-time manifold M. There are no coordinates in space-time. There are points. So you have a point P. It's a manifold, which means that locally is flat. Therefore, at least the neighborhood of P could be mapped to RD comma 1. Right? For this course, the manifold is RD comma 1. So that's the triviality. But this picture still helps you orient your mind. All right. So what is this map? This map is a coordinate system. It sends the neighborhood of P to a point to points in RD comma 1. So it will assign, the map is called alpha. It assigns the point x mu of P to point P. Right? It sends the point P to a point in RD comma 1. This assignment, this alpha thing is the map that assigns coordinates. There's no physics associated with that. That's made up, right? It's imaginary. It's in my head. And somehow the physics should reflect the fact that that is imaginary in my head. We'll see that. All right? So what a coordinate is, coordinate always presumes a choice of such an arbitrary map. Now, all right, let's keep track of these maps. We want to do a coordinate transformation in space, in this manifold. How are we going to describe it? Consider 2 points near each other. They're both in this vicinity. P prime is in the vicinity of P. First, I'm going to apply one map, one set of coordinates that sends P to XP and P prime to XP prime. Good. Then I'm going to apply another coordinate, X prime, alpha prime, that sends P to X prime P and then P prime to X prime P prime. A coordinate transformation is basically going from here to here. How do you go from here to here? You do alpha prime minus 1 alpha. So an abstract map between P and P prime is pulled into some transformation between these guys, right? That is what a coordinate transformation is. Now it makes sense to talk about the differentiable coordinate transformation because everything is defined in RD. Let's make sure this works. Because my next point will not work if this is not. Right? Here, all I'm doing is I'm just picking two different coordinate systems. It's called a diffeomorphism if these functions are differential. The function is differentiable and its inverse is differentiable. If the coordinate transformation, so again, coordinate transformation is made up in our minds, right? It's all in our minds. Coordinate transformation is called a diffeomorphism if not only it's differentiable, but also its inverse is differentiable. Good. All right. Now that we define what the diffeomorphism is, we're going to talk about two different types of diffeomorphisms: active diffeomorphisms and passive diffeomorphisms. Active diffeomorphisms are going to correspond to symmetries and charges and actions because we're doing something. Passive transformations are the redundancies of descriptions. It's the stupid fact that I have to describe points on a manifold using rulers and clocks. I have to use x's and x primes, right? So that is passive. There's no physics associated with passive transformation. Active transformations involve some physics. Good?
Can you say again how you describe the passive
I will describe it. But there are two types of diffeomorphisms we're talking about: active and passive. And this is something that is like gave me so much of a headache. Good?
So if I rotate my head, that's a passive.
That's an active transformation. However, if you are sitting there and I move here, so I see your head rotated, that's a passive transformation. That's a very good example. So you already, this already gave you what I need to explain. So his head was at point P, moved it to point P prime. The points on the manifold moved. I kept my chart fixed, my set of coordinates fixed. That was an active transformation. What was the other one? The point P was a point P. I was using x, then I used x prime. So I was using alpha, then I used alpha prime. The second one is passive, the first one is active. The first one is actually physical. Something is happening to the manifold. Points, things are flowing, with some crap is happening. The second one is just in my head. But you could talk about different diffeomorphisms in both contexts. Because these diffeomorphisms are about these, they're defined as with respect to these coordinate systems, right?
So, active ones like inertial frame changes, and then active ones
Are active ones are what?
like you have to include like fictitious forces.
No. So you don't. No. Let's not say that. I think that this topic is so confusing that I'm sure in some sense what you said could hold. I would not recommend thinking that way. I think maybe there's a way of thinking about it, but I honestly think every time somebody like in my mind this is how it works. I just need one way of understanding things, right? Maybe there's another way of understanding, but this is something that probably does confuse me a lot, and this is one way that I understand. Sorry about that. I wish I could do better. All right, so let's describe active diffs. These are same coordinate systems, same map alpha, but different points. P goes to P prime. Our friend's head moves, right? But we're still using the same coordinate system. the fact that I'm using the same the fact that whether I change the coordinate system or not doesn't tell you whether the transformation was passive or active, because you could combine the two, and it's kind of confusing. That's why it's actually confusing. All right, so let's move the point P to P prime and use one chart. Under the map alpha, P goes to XP and P prime goes to X prime. So here's a transformation delta X. Every time I wrote in the previous slide delta of X mu, this is what I meant. Good. This is what I meant every time. Now, all right. Now we see that as P goes to P prime, X mu of P goes to X mu of P prime. So I can write down X prime of, oh wait, yeah. I think I'm gonna do this, right? Because I'm moving it. Now I can expand X prime of mu in terms of X mu, and this is delta X. Good. Now here comes the catch. When I write phi of X, by my definition, this is not a field in space-time. The field was a map from points on the manifold to complex numbers. This is something else. What is this? This is, so phi tilde is the actual field. This is the pullback of phi tilde in the coordinate system, right? Because phi has to take as input point P. Sorry. Whoops. No. That was correct. That was correct. That's correct. Sorry. Phi of xp is phi tilde of alpha minus 1 of x. Right? Phi tilde is a function of p. What is p? P is alpha minus 1 of xp. This should be xp. Right? So the field is phi tilde, but we colloquially use phi of x, which is the combination of phi tilde and alpha minus 1. Good? Now at this point, yeah.
So what does the phi xp map to? Like eventually the phi tilde, right? So it takes the input from the real Euclidean space, and then takes the inverse, and then you apply the phi tilde to convert it to the real.
Let me just sorry. Let me say words and then tell me if I did not answer the question. So phi tilde, you can't differentiate, you can't transform nicely. What you do work with is phi, which is phi tilde alpha minus 1. Now phi is a function. So now you could talk about, now you see p going to p prime corresponds to xp going to xp prime, corresponds to some delta x. Now you could talk about how function of how phi changes under delta of x. It's a function. That's what you do, right? Here's phi of x prime, written as phi of x plus delta of x, which is phi of x plus del mu of x, del mu of phi. So already you see that del mu of phi depends on my coordinate system. As it should. Vectors should depend on my coordinate system. If I rotate, the components of the vector change. But I haven't done anything. Good? So I'm describing to you what tensors are. And I'm describing to you that physics should always be written as a bunch of tensor equations. So that it's independent of the coordinate system. An example of an active transformation is a Lorentz transformation. X prime of mu is lambda mu nu x mu plus a mu, right? These are nice because they're the isometry. So what is an isometry? It is a diffeomorphism that preserves the metric. Another way of saying is that it's a diffeomorphism that keeps the distance in there. I haven't told you what the metric is, but hopefully. So you see, there is a notion of distance between P and P prime. The notion of distance has to be defined as we pull these points to your coordinates. There is a notion of distance, that's a metric, that also has two indices, mu, because it will depend on my coordinate system. And the fact that there is that notion of distance will be invariant under the some transformations that leave them distance invariant stand out. They're called isometries. Good. All right. I want to make a pause and just ask your questions because the next step I'm going to talk about passive and it's going to get confusing. So, are the active transformations clear?
So the active transformation is the transformation.
Yeah, something is actually happening on the manifold. So physics happens on the manifold. The rest is in my head, right? This phi mu of x and all that is my way of describing it. It's me seeing the phenomenon, describing the phenomenon of P going to P prime. Yeah.
The other thing is that I still don't understand when you say, okay, let's consider a real field that goes from M to R, and then I take phi without the wiggle, which I take to be the complex field we defined earlier.
That's because it's not complex.
No, but then you have phi of xp is equal to phi naught wiggle.
Oh, that's not phi naught. That's phi O. Sorry. That is phi tilde O composition alpha minus.
Yeah.
Composition. Sorry, it's not tilde. My bad. It's not O. That's my attempt at writing composition. Thanks, Raz. All right. So always keep this example in mind. The head rotating. Something is actually happening, right? As opposed to the other picture is like the passive that we're going to describe. That is not like that. All right. Good. So the case of charges, conservation laws, and all of that is going to be about this stuff. There are advantages to using the passive picture. You will see that at some point. But in physics, I also use passive picture quite often. So it's important. That's why I'm actually going over it. Now, what is the passive picture? It's same P, different coordinates. Now I'm talking about x mu of P and x prime mu of P, describing the same point. The physics should not depend on coordinates. All right. So let's go back to what we had. Phi tilde is my field. I can talk about phi of x of P, which is phi tilde composed with alpha minus 1. Or I can talk about phi prime of x prime of P, which is phi tilde composed with x prime alpha prime. Good. Something important happens. Do you see what is happening? What I would like to do, sorry. Yeah, that's one example of coordinate transformation, change of coordinate things. But I have to make sure that the physics does not depend on coordinates. How do I do that? The way I do it is that as I change my coordinates from x to x prime, I also transform the field from phi to phi prime to make sure that nothing changes, right? So I must satisfy this property that phi of xp is phi prime of x prime of p, so that the total variation is 0, because nothing happened, right? It's all in my head. Now, this already gives you an example of a transformation which combines field transformation and space transformation. So if at first it sounded weird, why are we combining the two? Why are we talking about this? You generically have these setups. So now the generic setup is a physical transformation that also involves a change of coordinates. So in principle, we'll combine everything. And in physics, it always comes up like that, right? But a transformation is passive if delta phi is 0, not a big delta phi, right? So that big delta phi is crucial for us. We want to talk about active transformations. If that's why I talked about symmetry making some delta phi non-zero, resulting in delta of S 0. Right? I first say make it delta phi. That's non-zero. If this was 0, there's nothing to discuss. That's just stupid coordinate transformation. So symmetries involve first this being non-zero, having resulting in delta of S. That's why we talk about delta. These delta is important here as well, right? You have to talk about the delta. Just make sure we're talking about an actual honest to goodness transformation, active transformation. So one way of seeing that the transform this is 0 is for passive transformations. You have this thing, the del mu of phi of delta of x mu. Wait a second. Oh, del mu of phi times delta of x mu is minus del mu of phi of x. This is just to ensure that nothing has happened. I don't want to stress this actually. All right. So now that we understand passive and active transformation, maybe I should ask a question. Oh, maybe I should not ask for questions because I'm running. The class is until when?
45.
For. Ooh. Well, quick questions. All right. Scalar field is a setup. It's so sorry. Let's go back. Now let's talk about the transformations of the field under spatial transformations. When we say a field is a scalar or a field that has a particular representation, it means that how should the field, I'm telling you, how should the field transform such that it can cancel the effect of this, right? So this equation you saw was for a scalar field, right? Sorry, this equation with phi equal phi prime. So this is the actual equation. Whoops. It's the actual equation. If you could satisfy this with phi equal phi prime, that's the scalar field. No, actually, that's not how I want to say it. My bad. Sorry. That's not how I want to say it. Well, this is how I want to say it. If you could satisfy this equation like this is a scalar field because delta phi is 0. But it's possible. How do I say it? Actually, wait a second. Yeah. Okay. Here things get a little bit funky. So, what did we define? We defined the field all along. I've been talking about the field being a function from the manifold to complex numbers. That's the scalar. Everything I said about that is a scalar field, and I just told you that this capital delta phi is 0. You could have non-scalar fields. These are the fields that you have to specify a little bit differently. They're delta phis. We'll see how they transform. So the delta phi is about how they transform under Poincare transformation, under the isometries of the space time. So, for example, here what happened was that. Well, I think I'll give an example. I think that saves this part. So let me not comment on scalar versus not scalar for now, because I'm going to give examples and that makes it clear. Let's just make sure that this clicks. Good. All right. So what we're going to do is we're going to make some delta phi and see how delta, what the total delta L is and what's the total delta S, right? So to see what the total delta L is, in general, delta involves a change in the field and a change in the coordinates, right? So we're going to do both of them. And delta S is going to be L minus delta L minus this guy, right? So let me skip this because I have not explained this at all. Yeah, I'll explain this next time. Good. Okay. Here we go. All right. So here's delta L. What we have to do is, so the L is a function of phi A, right? And del mu phi A. So as I make a change, I have to talk about delta phi A and delta del mu phi A. So the way it's going to work is if I want to see the total variation of the Lagrangian density, there will be a term coming from the derivative with respect to phi A. This is the internal transformations, for instance. Well, that doesn't, yeah. And then the total variation of this guy. And it's possible that this Lagrangian density has explicit x mu dependence as well. That's not common, but that's also a possibility. Good. So each of these transformations is a combination of space-time and internal transformations that we had these relation for. This relation for, where was it? We had this relation, right? You plug in what delta phi A and this guy is. You bring del mu out of this, you expand it, you obtain the following equation. This is a few lines of algebra. So you obtain the variation with respect to phi A, the variation with respect to derivative of phi A, plus a total derivative. We already encountered this total derivative when we were doing the Euler-Lagrange equations. I went through it very fast back then. This is the total derivative. Now, these two terms you recognized before, right? These two terms cancel by the Euler-Lagrange equation. All that's left is this term that I can write down as a boundary term. So here's what I'm left with. So the total variation of the action under transformation is a boundary term. Good. Previously, what we did was that we dropped this term by taking the boundary to infinity. And then we said, oh, well, the Lagrange equation is full. Here, what we're going to do is that we know that for certain transformations, the boundary term will vanish. If you have several boundaries, like this and this, they cancel. Right? All right. So this is the object of interest. And here we're going to do integration. Here, instead of taking the boundaries at spatial infinity, we're going to take them at a constant time, right? From some Ti to some Tf, like this setup. You could introduce this guy. You could introduce this theta mu nu, which is basically, well, actually, yeah, it's basically repackaging. It's a repackage. You could repackage these terms in this form. I absolutely encourage you guys to go through this step by step. I won't unfortunately have to. I know that I'm not doing a good job of going through every line of it, but I'm sort of in a time crunch. So these lines of algebra, I absolutely encourage you to reproduce. So you introduce this theta mu nu operator. That's just a definition, if you wish, to write down delta of S this way. All right. this is going to be related to our conservation law. Good. So let me recap. I went through this way too fast. I took my Lagrangian density. It's a function of phi of A and del mu of phi of A. I considered total variation of phi of A, delta phi of A, and total variation of del mu phi of A. I took derivatives and expanded. Repackaging everything, I found a bulk term that happened to be the same bulk term that I found in Euler Lagrange equation. It vanishes. I end up with a boundary term as well, right? So far, I didn't see a single word about symmetry. I just said a general transformation. So we'll have to see that this guy vanishes. So this is delta of S. I think I said this. Now, what happens is that if you have a symmetry, delta of S vanishes, which means that this integral should vanish. Right? Okay. So here's that integral. To see what's happening is that if you recall this capital delta phi of A, I introduced these epsilon i's. I think I erased them, right? For independent variations. Once you plug them back in, you obtain these equations. Let me just write them on the board quickly. So the variation of the field delta phi of A was sum over I epsilon of I think I called this phi of A, capital. And then the delta of x mu, the sum over I. Good. And delta of phi has both of these two terms in it. That's why I have epsilon i's. I take epsilon I all out, and I obtain this expression. Now, if delta of S is 0, the kernel must vanish.
It's always true.
It's not always true. It's only true if it's a symmetry. Symmetry was defined as some delta of L that gives you delta S equals 0. So I wrote what delta of S is. Now I go back to my assumption of symmetry. Delta of S has to be 0. Therefore, the integrand has to be 0. Because I can choose these guys as I wish. Right? I can make arbitrary formations and arbitrary surfaces. Right?
Synchronize with the key vectors.
Epsilon i's are the killing vectors. You could view them. Yes, you could view them that way. All right. What is this guy that has to vanish? It has a name. We're gonna give it the name, current density. Right? So now the game is pretty obvious. No, actually, I haven't proved to you that this is conserved. So say it again. Say it again. This guy up there.
Yeah.
Okay.
That shouldn't be like shouldn't be the other.
Oh,
Yeah,
little curly one.
Yeah, because the leading is small.
Yeah. I think I wrote it here. Yes. Thank you. All right. So we define this operator. It's a density. It's a current density, right? That on all these surfaces, it should integrate to 0. This is only possible if it satisfies the following conservation law. this is basically Stokes' theorem. So I'm gonna go over it, but let's just first see the logic is clear. I know that I went through this way too fast and I did poor job. I'll try to review it better next time. But this integrand will have to vanish. We're gonna give this a name, j mu of I. The fact that it's 0, one way you could check to make sure that this is satisfied is that if it satisfies this current conservation law. However, if this vanishes, it must satisfy this. As I'm going to argue using Stokes' theorem. A second. All right. Well, actually, am I going to argue using Stokes' theorem, or is it obvious?
Is it not through the divergence theorem?
Yeah, it's basically divergence theorem. Stokes' theorem is the divergence theorem, right? It just basically says that if you have a current, which if you have some current, J mu, where del mu of J mu is 0, right? The integral of that current on any boundary will have to be 0. That's the Stokes theorem. Now, if you introduce two boundaries, Q initial and Q final, they will have to cancel. This was the Noether's first theorem. All right, I have about 10 minutes left. I did such a poor timing this time. I'm going to go through a bunch of examples. Hopefully the example would make this quick step a little bit clearer. All right, so the first example is a space-time translation, infinitesimal space-time translation. Here it is. X prime of mu is x mu plus epsilon mu, which is x mu plus delta mu I, epsilon I. This is an isometry of the Minkowski space-time. Here's my x mu I. Phi IA is 0. Why? Because I'm taking, scalar. Because I'm taking the scalar, right? All right. That you already see. If it has a no mu nu indices, it must be scalar, right? You also see that fields that are not scalar would transform non-trivially under passive transformations, right? This is the thing that I didn't want to say when we're earlier because I thought like I have to separate them, right? So fields that have that transform, they don't have like that non-trivial spin. They're not functions on the manifold. They live on this. They live relatively on these charts and coordinates that we have described, right? Is that good? Under passive transformation, alpha mu or vector changes. That should be clear, right? There can possibly be a meaning. Yeah, okay. Good. Let me say a few more words about this. I think I know that I'm running out of time, but so here's your manifold. Oh, here's a flat. Here's P. Here's P prime. Right? There is no coordinate independent way of talking about a vector sending P towards P prime. Hopefully that's clear. There is no coordinate independent way of saying which direction a vector is pointing. The vector is defined always in this space. So on this map that is pulled using alpha to sum on, right? So these guys transform under my passive coordinate transformation. It's only the scalar field that was special, right? So delta phi for scalar, capital delta phi for scalar field is 0. For these fields, delta phi is not 0 for passive transformation. Good. All right. At least I explained one thing. All right. Space-time transformation. So here's a scalar field. Very good. Here are my my transformations, right? I had a formula for J mu I. I just copy pasted it here. Here's what it is. And if I plug in the values that I had here, phi of A on I is 0. So I'm just only left with this guy. This is delta mu nu. The corresponding current here for space-time translation is precisely this minus theta mu nu. Now something funny happened. This is called energy momentum tensor. It's the current associated with space-time translations. And what do you get if you integrate over a constant time slice? Which is momentum, right? The zero component of momentum is Hamiltonian. If you integrate it over a time-like surface, it's momentum. So earlier when I asked, do you know cases where we integrate charge currents over like something that's not space-like? Here's momentum is one example, right? This is called energy momentum tensor. Two funny things happen. First, this energy momentum tensor showed up in our analysis of an arbitrary transformation as a term, right? That's one thing. That's something to keep in mind. That's why I gave it a name, and I realized at the moment that, oh, this is too early to say that. Second is this. What symmetry did I use to define energy momentum tensor? Only translations. This is very, very important. So classical physics, non-relativistic classical physics, right? Is there an energy momentum tensor with like four coordinates? Yes, there is. Is it conserved? Yes, it is. I'll tell in a second where relativity sneaks in. Because these translations are translations that are exist in non-relativistic theories as well. I don't need Lorentz symmetry to define stress. However, and it's conserved. It's a conserved charge. However, oh, oops, I did not say that. Let me see. Oh, it's later on. All right, let me just jump here. Now, that was a translation example. Now let's take Lorentz transformation as a second example. So here are what the transformations are. Infinitesimal, you could write it as this antisymmetric tensor with two legs, omega mu nu. You absolutely have to do this at home, like later, to fill in the details. Here's what the omega mu nu is. It's antisymmetric. Now, as we said before, these transformations act trivially on scalar fields, right? But on vector fields, they would do something non-trivial. All right. Here's what how they transform. That's not the point. Here's the point. Actually no. Wait a second. Oh yeah, here. That's right. Let me skip here. Good. Good. All right. A general field will transform the following way. As you send x mu to lambda mu nu x mu nu, the field will transform to phi prime, and phi prime is some matrix acting on phi, right? So this is the way you can think about it, is that phi has a label, phi of A, right? And that matrix, what did I call it? S of lambda has A, B indices. Notation-wise, we often write it this way, right? These are when the actions. So here's I'm defining you what it means to talk about the representation of the Lorentz group. A field transforming a representation of the Lorentz group. If the field could be written as a vector with a bunch of indices, such that when you apply the Lorentz transformation to like x mu part, The phi prime part will be matrix multiplication in the spaces. Then it transforms as a representation of the Lorentz.
What about the coordinate? I'm not sure about it. Like phi prime you are defining at some new position of x, right? X mu prime is it? And the right hand side also, the coordinate should be x mu prime. Right?
No. So the equation. So previously for scalar field, I wrote this equation. Well, no, not for scalar field. This is the grand thing. For passive transformation, this is what we have, and that's what I'm describing, right? For scalar field, here what happens is that as you do a Lorentz transformation, these are passive transformations in my head. I have to tell you how this guy transforms. And that's how it transforms. Then it transforms under Lorentz particular representation of Lorentz group. Let me just finish this thought. All right. Good. So this is supposed to be a symmetry. You could linearize this guy. You get a generator for it, J mu nu. You plug it into the equation that for a conserved current. You find the conserved current density. It's actually related to the stress tensor, but it has these x's multiplying it. If you write down the conservation law for this, you obtain that this is guaranteed using the fact that stress tensor was conserved, plus now in addition, it has to be symmetric. So this is, I guess I ran out of time. I didn't have time to do this, but as a homework, you could do this, right? So the lesson is this. Spatial translation and time translation in non-relativistic field theory define for you stress tensor that's conserved, right? And it has time and space components, right? It's a stress tensor, that's all sorts of things, right? That's perfectly fine. If you add to it Lorentz transformation and the symmetry of relativistic field theory, the corresponding currents are still related to the stress tensor. Now the conservation law, on top of the conservation law that you had before, requires stress tensor to be symmetric. Right? So that is relativity. That's an important consequence of relativity. There's a longer story I'll tell later, and I ran out of time. I didn't have examples here. I have to give examples of how vector fields transform. And I will stop here for today. Yes?
When you find those generators of the Lorentz transformations, those will turn out